All right, good day, everyone. Welcome to our YouTube lessons with chemistry with the analogous. I'll be looking at chemical equilibrium today. So I'm looking at a very crucial topic to O level and A level students. But basically, this equilibrium video will be for the O level students. So chemical equilibrium. Now, I'll quickly do a brief intro of chemical equilibrium and I'll quickly look at equilibrium constant. That'll be the main focus of this lesson, equilibrium constant. Now, chemical equilibrium is actually a dynamic equilibrium, or it's an equilibrium encountered in chemical changes or in a chemical reaction. They are usually occur in closed system, especially when they are gaseous reactants. So what do I mean is this? For instance, A plus B gives react to give C plus D. So A plus B reacts to give C plus D. Now, if A plus B reacts to give C plus D, and A, C, and D react in the same manner to give A and B, there will be a point. There will be a point during the reaction where the rate at which A plus B is reacting to give C plus D will be equal to the rate at which C plus D is ready to give A plus B. So at that point, A plus B is ready to give C plus D, and at that same point or at that same rate, C plus D is ready to give A plus D. At that same rate, we will say we have established equilibrium. What type of equilibrium have we established? Dynamic equilibrium, because the equilibrium is not static, it's not in one place, it is moving, and it is best established in closed system. In closed system. In closed system. Now, for those of us writing UTME, if for instance I want to write the equilibrium constant of this equilibrium reaction, especially the equilibrium constant of the forward reaction, the equilibrium constant of the forward reaction is usually the concentration of products, not just the concentration of products, the active masses of products over the active masses of reactants. All these were proved with Gobbe and Wage law. So in other videos, I'll show the proving of equilibrium constant. I'll show a subsequent video. I'll show the proving of equilibrium constant. How to get this equation. But basically, for the forward reaction, it's usually the ratio of the product over the ratio of the reactant. Now, also, this is the equilibrium constant for the forward reaction. And equilibrium constant, basically, equilibrium constant K, some call it KEQ, affect only gaseous reactants and aqueous reactants. When I mean aqueous, this is not special. So what I mean is that when you are writing an equilibrium constant expression, you should watch out for the species having gases and watch out for the species having aqueous. So either it is aqueous or gases. That's when it can we can determine the equilibrium constant. That's when it can affect the equilibrium constant. Now I will show you a simple equilibrium constant problem and how to solve it. All right, now for equilibrium constant for this reaction, to write the equilibrium constant expression for this reaction, using this Gobbe and Wade derived expression, or this expression derived from the Gobbe and Wade equation, or the law of mass action, we can observe that N, M, X, and Z are reaction coefficients. So to write the equilibrium constant for that reaction, we'll say the product side. So the product for the forward reaction, remember this is the equilibrium constant for the forward reaction, which is the one they will ask you in UTME or WAEC level. So it is C raised to power X, then D raised to power Z. Now the coefficients. Now all over A, now concentration of A raised to power N. This concentration of A raised to power N is called the active mass of A. Active mass, the concentration of a reactant raised to the power of its number of its mole is active mass. Then B raised to power M. As simple as that. Now, for the reverse reaction, it's going to be, for the equilibrium constant for the reverse reaction is going to be opposite of this. So it will not be, this ones will be up now, this ones will be, so for the reverse reaction to be opposite. Now, because equilibrium constant of the reverse reaction, those of us writing work, you might not need to know this, or a UTM, you might not need to know this. For the reverse reaction, it's going to be opposite. This one is K for forward reaction. No matter when they say equilibrium constant in general, we refer to this one for the forward reaction. Though for the reverse reaction, we can have it to be this set, A raised to power n, B raised to power m, C raised to power ox, D raised to power z. So this is equilibrium constant for the reverse reaction. Now it should be noted that equilibrium constant for the forward reaction, for the reverse reaction, is 1 over that of the reverse reaction. And for the backward reaction is 1 over that of the reverse reaction. And this is your UTME part. The equilibrium constant of the backward reaction multiplied the equilibrium constant of the forward reaction equal to 1. That should be noted. Please take note of that. That should be noted. Now I'm going to take examples from UTME level and from SSC level. Now, this question says, write the equilibrium constant expression for the above reaction. So this is my reaction above. I'm about to give you an equilibrium constant expression. I said when you normally ask such question, it means they usually refer to the forward reaction. So equilibrium constant, I said before, it affects only gases. Please take note, gases and dissolved species. I mean aqueous. So this is gas, this is gas, this is gas. So they will all be expressed in the expression. So I will say SO2 raised to power 2, O2 raised to power 1, all over SO3 raised to power 2. That's all. Now, please take note. This is all. This is the equilibrium constant of the forward reaction. As simple as it is that simple. Is that simple. Now, I'll replicate some complex ones found in the UTME pack. Now, what will be the equilibrium constant expression for this reaction? Now, for this reaction, you can see that this is solid, and this is gas and gas. The equilibrium constant in the equilibrium constant expression, solid and liquid are taken as unity. When I mean unity, one. So what I mean, they don't affect equilibrium constants. They don't affect equilibrium. It is difficult to monitor the equilibrium of solids and liquids. It's very difficult to monitor the equilibrium. So, for instance, I have. For instance, I have this I have K to write K, so I can say H2 raised to power 4. Yeah, the product times 1 unity all over. We don't use Fe, so Fe is 1. Then H2O raised to power 4. So it's more like saying H2 raised to power 4 all over H2 raised to power 4. That is how to write the equilibrium constant expression of reactions. So I can just put a simple. Now you will see the answers like this. Yes. So now let me put a more technical one that have both liquid, solid, and gas. So let's use this reaction. I place Fe in. I said Fe. Let me use Fe again. I place sodium metal. Yes, solid in cold water. It's cold water and liquid. And let's say it happens in a closed system, and we got NaOH plus hydrogen gas being liberated. Now the NaOH you got was aqueous. Aqueous NaOH, hydrogen gas was liberated. So let's balance the equation. Let's try and get a balanced equation. So let me see if I can get a balanced equation. Okay, Na balance, hydrogen is not balanced, so it's more like say 2 2 2. I think it is balanced now. Yeah. So now let's try and get a balanced equation. What's a balanced equation? Let's try and write the equilibrium constant expression. The equilibrium constant expression is going to be, now those for solids and liquid will not be expressed. They are taken as unity one. So to write this equilibrium constant expression, assuming this reaction goes to equilibrium, it's going to be NaOH raised to power 2 multiplied with, these are products, H2, active mass of H2 raised to power 1 all over 1. This is the answer. As simple as it looks. This is how to write the equilibrium constant expression. Sometimes it's referred to as KEQ. Yes, KEQ. So I'll quickly drop some important info about equilibrium constant. Some very important info about equilibrium constant. And one thing that can affect equilibrium constant is temperature. Yes, one thing that can affect equilibrium constant is temperature. Temperature. So I'll quickly say this. Now I'll use a simple reaction to explain. So let's take, for instance, the Haber process. The Haber process, 2N, or rather, pardon, N2 gas plus 3H2 gas. Yeah, and to give 2NH3. Now, we all know that this process is exothermic at delta H of around about 645 kilojoules. Yeah, around this range. So this is the Haber process. This is the Haber process, a simple Haber process having this delta H, having this base enthalpy change. Now, please take note, when enthalpy change is negative like this, the reaction is said to be exothermic. So this reaction is exothermic. That means it liberates heat to the surrounding. So if delta H was positive, this reaction would be, what's it called now? Endothermic. That means if I had just 645 or a positive 645, delta H was going to be, or the reaction is going to be what now? Endothermic. But as it is negative, the reaction is exothermic. So if I have an exothermic reaction like that, now how will temperature affect this equilibrium constant? Now, all equilibrium reactions, the third reaction is either exothermic or endothermic. There's no reaction that does not have heat change. So every reaction has heat change, have an enthalpy change. So for this exothermic reaction, now it should be noted that um, uh, um, the greater the equilibrium constant of the forward reaction, the greater the equilibrium constant of the forward reaction, the greater the yield of the product. So in my next video, I'm going to do Le Chatelain's principle, how temperature and how temperature, concentration, and pressure affect equilibrium constant. But I'm saying something: the higher the equilibrium constant, the more the product yield. So if the value, if assuming the value of K is 0.5 and the value of K for another reaction is 2.5, the reaction that have K of 2.5 for its forward reaction has more product yield. That means you obtain a better product in that equilibrium reaction than when K is 0.5. So you should be taking it. So the greater the equilibrium constant, the more the product yield. Thinking that is a UTME question. Those of us in Nigeria writing UTME, I saw that in your past questions. Also, I'll quickly talk about equilibrium constant. Now, I'll quickly say this. For exothermic, please just cram it down. If you cram it, now for K, if you cram it or you learn it, you are yet to learn, so you learn it. For exothermic reaction, please take note, an increase in temperature decreases equilibrium constant. An increase in temperature decreases equilibrium constant. Please take note, for an exothermic reaction, an increase in temperature decreases equilibrium constant. Please take note, an increase in temperature decreases equilibrium constant for exothermic. Why? Increase in temperature for exothermic reaction decreases the product formation. So increase in temperature for exothermic reaction increases the yield of the reactant. So the equilibrium constant before the reaction decreases. Please take note of that. Now, for endothermic reaction, so assuming this reaction is endothermic, so let's say we have a positive 500 as the enthalpy change. The fourth reaction is endothermic. So for endothermic reaction, increase in temperature, decrease, or rather, pardon me, increases this time equilibrium constant. So temperature affects equilibrium constant. Please, you should note that an increase in temperature increases equilibrium constant for endothermic, while for exothermic it is the opposite. Increase in temperature for exothermic, now exo decreases the equilibrium constant. So with this video, I know you must have learned a lot from equilibrium constants. I remain analogous. I will urge you to always watch our video, subscribe to the video, share it with your friends, especially those of us in O level and the A level series. Share it with your friend. You study courses pertaining chemistry. This is a channel that will help you throughout your university, throughout your preparation stage for any examination. So God bless you. I will see you in subsequent videos.